In our last lesson, we covered variables and functions and systems, and introduced the concept of spaces. In this video, we're going to build toward an understanding of Euler's formula. Some of the steps along the way are going to seem a bit disjointed, but they're all fundamental concepts necessary to our goal. First, we're going to need to look at the concept of exponentiation. Exponentiation is a shorthand way to conceptualize and write multiplication of like terms. For instance, 2 times 2 equals 4 can be written as 2 to the second power equals 4. The general form of exponentiation can be written as b to the n equal to b times n b's. I'm using the letter b as my variable to remind myself that we call that term the base of the exponent. N is called the power of the exponent, or just power, or just exponent. Part of the advantage of dealing in exponents is that math gets simplified. I'm going to state a few of the important results of this identity. If you're unfamiliar with exponents, plug in some numbers and evaluate by expanding the exponents to prove it to yourself. Next, we will look at the concept of complex numbers. Complex numbers have both an imaginary and a real part. So far, all the numbers we've been dealing with have been real. We choose them from the real line, represented as a continuous line from negative infinity to infinity, and the script r for real. You can think of the real line as the space from which real numbers are drawn. They are subsets of the real line, the most commonly used being real integers. So what is an imaginary number? We know that the square root of 4 is equal to 4, and that 2 squared is equal to 4. The square root of 1 is equal to 1, and 1 squared is equal to 1. The square root of 0 is equal to 0, and 0 squared is equal to 0. But what is the square root of negative 1? The result, if squared, should equal negative 1. But a fundamental mathematical definition that a negative number multiplied by a negative number results in a positive number won't allow this conception. So we will need to expand our mathematical vocabulary to include this new concept. We're going to call the square root of negative 1 an imaginary number, and represent it by the lowercase script I. We call any real number multiplied by I imaginary. A couple important results of the imaginary number identity are that I times I is equal to negative 1, and that 1 divided by I is equal to negative I. Similarly to the way we described real numbers as being drawn from the real line, we conceptualize imaginary numbers as being drawn from the imaginary line. As stated earlier, a complex number consists of a real number and an imaginary number. So if we conceptualize the real number line and the imaginary number line as intersecting perpendicularly, we can think of a complex number as being drawn from any point in the plane we have created. You need to differentiate what I've drawn here from previous plots where we represented a function as a relationship between the axes. In complex functions, we think of this plane as taking the place of one of the axes. Let's look back at functions and systems and see how this all fits together. For the functions we'll be dealing with, our input will be real and our output will be complex. So imagine we have an input x drawn from the real number line going into a function, and the output will be drawn from the complex number plane as represented by c. Let's say the operation consists of raising I to the x power. Let's write a table with a few sample points to illustrate our real and imaginary parts. Once you recognize the pattern, it's time to sketch the function. We have a new dilemma now, which is that our two-dimensional plot used previously cannot illustrate our function. And we have two clear options. We can either sketch the function in 3 dimensions, or as 2 plots side by side representing the real and imaginary parts. The latter is far easier to do by hand, and is by far the more common. Even when sketching in 3 dimensions, I prefer to sketch the projections of the function onto the 2D planes rather than the line in 3 dimensions. I think it's a bit clear. Either way, they both represent the same relationship between the domain x, which consists of the real number line, and the range c, which consists of the complex plane. Remember that the function is continuous, so we have drawn it as a continuous line. Next, we will look at coordinate systems. When we discussed plots before, it was explained that plotting is just a way to relate the domain and range of a function. We use the Cartesian coordinate system in our examples, because the understanding of it arose naturally from our function. Remember, in the Cartesian coordinate system, what we are doing is conceptualizing a table with input and corresponding output values, and marking what point in the space has those two values. The polar coordinate system is also commonly used. In the polar coordinate system, we describe the points on the plane using its distance from the origin and the angle from the positive input axis. Any point in planar space can be located using only these two pieces of information. Polar coordinates can be less intuitive, but using them can make the number crunching we do significantly easier. In particular, we're going to need a conceptualization of polar coordinates to understand sinusoids. Our next task is to introduce the concept of the unit circle. Let's say we have a circle. We can measure the diameter of the circle and the circumference of the circle. These two variables are obviously related, and no matter what size the circle is, the relationship remains the same. We designate the relationship of the circumference divided by the diameter of a circle as the irrational number pi. Now let's examine a circle with a diameter of 2 centered on the origin of a coordinate system. We call this the unit circle, and use it as a touchstone for a great deal of mathematical conceptualizations. If we wanted to calculate the circumference of this unit circle, we just look at our definition of pi, isolate the variable circumference, and plug in the known value of the diameter. The circumference is 2 pi. Now let's say that we want to describe a point somewhere on this unit circle, using polar coordinates. We need the distance from the origin and the angle from some fixed line, which is pretty much always the positive horizontal axis. We know that the distance from the origin to any point on the unit circle is always 1. So to describe a point on the unit circle, all we need is the angle. You may be most familiar with degrees as the unit of angles. We will be using radians as our unit of measurement. Radians are defined as the distance traveled along the unit circle from the positive intersection. Let's arbitrarily label our axes x and y. We call the intersection at x equals 1, 0 radians. Radians is the distance traveled around the unit circle, so by the time we are at the intersection y equals 1, we have traveled pi over 2 distance. At x equals negative 1, we have traveled pi distance. And at y equals negative 1, we have traveled 3 pi over 2 distance. And by the time we've made a full rotation, we've traveled 2 pi distance, which we calculated earlier as the circumference. Note that the point on the unit circle represented by 0 radians and 2 pi radians is the same. The unit circle allows us to conceptualize sinusoids, which is our next step. Let's look at a right triangle with angle theta. Name the sides relative to the angle theta as opposite and adjacent. Angle theta is related to the ratio of sides by the sinusoid functions. Specifically, sine of theta is equal to opposite over hypotenuse, and cosine of theta is equal to adjacent over hypotenuse. We can imagine these definitions as systems, though I have no idea what operations a calculator does to theta to output the ratio of sides. Now let's look back at our unit circle. Say we know the location of a point, Q, on the circle in polar coordinates. The distance from the origin is 1, as is any point on the unit circle. And let's represent the angle as a lowercase t. We want to know the Cartesian coordinates. To do this, we'll use our sine and cosine functions. The sine function will give the x-coordinate, and the cosine will give the y-coordinate. Now let's create a coordinate system to illustrate the relationship of sinusoids to the unit circle. In our new plot, t is the input. We can plot both the sine and cosine function on the same coordinate system because they both relate the same two spaces. When plotting the cosine function, what we're imagining is the value of the x-coordinate of point Q as the angle t increases from 0 to 2 pi. In the case of the sine function, we're imagining the value of the y-coordinate of point Q as t increases from 0 to 2 pi. We also know that the angle 2 pi describes the same point as the angle 0. and that after a full rotation is made by t, the relationship repeats itself. Let's create a table and write out a few sample points. All we need to figure out is what it looks like until the angle t has gone around the circle once. You'll notice that I'm connecting my sample points with a smooth curve. I'm doing that because I know what it looks like if I took a bunch more sample points. If you're not familiar with the function, take more sample points. Note that the sine and cosine of t look very similar, just offset from one another along the input axis. Remember that sinusoids are just a type of function. Also remember that functions are just a set of operations on an input. What we've looked at so far are the simplest forms of sinusoids. The general form of a sinusoid is any function that can be represented as a times sine omega t plus theta. A, omega, t, and theta are all variables and could potentially be inputs to a system, but we will generally fix a, omega, and theta as constants and call them parameters. There are a few different ways to conceptualize how the relationship between the input and output changes when the parameters change. The most straightforward is the amplitude. By default, a is 1, which is the radius of our unit circle. You can think of a change in amplitude as a change in the radius of the unit circle. Let's make the parameter a equal to 2. The result is that the output of the system now has bounds, plus or minus 2. We could also say that we've expanded the range of the system from the space of any real number between -1 and 1 to the space of any real number between -2 and 2. The default of the theta parameter is 0. Theta is the angle from the positive horizontal axis on our unit circle that we start the function at. You can think of it as a shift of the function along the t-axis. Let's make theta equal to pi over 2. When t is 0, the argument of the sine function is pi over 2, which gives an output of 1. When t is pi over 2, the argument of the function is pi, which gives an output of 0, and so on. If what we've plotted looks familiar, that's because sine of t plus pi over 2 is equal to cosine of t. Now let's see what happens when we modify the frequency, omega. But what is frequency, anyway? Let's define period first. The period of a sinusoid refers to the amount of input units before the output repeats itself. We've seen that the default period is 2 pi. Frequency is defined as the inverse of the period. The default frequency is 1. You can think of frequency as the speed at which we're traveling around the unit circle. As our example, let's make omega equal to 2. So we are traveling around the unit circle twice as fast as default. When t is equal to 0, the argument of sine is 0, and the output is 0. When t is equal to pi over 2, the argument of the function is pi, and the output is 0, and so on. We have a problem now. Our sample points did not give us enough information for our plot. We're going to have to increase the number of sample points we take in the interval between t equals 0 and t equals 2 pi, or have the same number of samples, but in a shorter interval. The latter requires less work. If t is pi over 4, the argument is pi over 2, and the output is 1. The best way to gain fluency in sinusoids is to just do a lot of playing around with the parameters and sketching, and try to keep in mind all the different ways to conceptualize what's going on, because certain ways will be easier for certain things to build on in the future. We now have the tools to introduce Euler's formula. Right now, we are going to state Euler's formula because it ties together all the concepts we've introduced so far. In the next couple videos, once we've introduced calculus, we'll have the tools to circle back and prove Euler's formula. Euler's formula states that e to the I theta is equal to cosine of theta plus I times sine of theta, where e is known as Euler's number and is an irrational constant approximately equal to 2.72. Let's look back at the unit circle. This time, however, we're going to place it in the complex plane. What we're saying now is that the real part of a given point, represented by cosine of theta, added to the imaginary part of a given point, represented by sine of theta, describes a point on a unit circle situated in the complex plane and can be equally well described by e to the I theta. Basically, e to the I theta is a polar coordinate system for the complex plane. It completely describes any point along the unit circle. If you wanted a point beyond the unit circle, you would simply need to multiply it by a constant. What if we wanted to isolate and examine just the real part, cosine of x? We start with the general form of Euler's formula. Then we look at the circle and see that the polar coordinate e to the negative ix is equal to cosine of theta minus I sine of theta. We add the equivalencies, which gets rid of our sine term, then solve for cosine of x. Using a similar method, we can show that sine of theta is equal to e to the I theta minus e to the negative I theta divided by 2I. And now for our summary. We covered exponentiation, which is just a shorthand for multiplication. Complex numbers consist of a positive and imaginary part. The imaginary part can always be reduced to I times a real number, where I is defined as the square root of -1. We looked at Cartesian and polar coordinates and their relationship. We covered the unit circle, which we conceptualize as a circle of radius 1 centered at the origin of a plane. We covered the units of angle we'll be using, radians. And we introduced sinusoids and their properties, and bowed our heads to Euler's formula.